Hello everyone, welcome back to your next lesson. So this is your third video lesson of Unit 6, right, which is trig identities. So we have done so far in Unit 6, as a quick reminder, excuse me, we've learned the identities, right, and you've worked a decent amount, hopefully, with some of the identities and recognizing them, and that's going to be important through this lesson as well, and just kind of thinking through them, especially we talked about the Pythagorean identities. Recognizing where those come up. And with that, we did simplifying as well as proving, right? And just making sure you're using legal math there. So I encourage you to, hopefully you completed last week's homework, but I encourage you to go back and just practice those and check those over and just continue to do some repeated practice with it. And that will come up, and these identities will come up throughout this lesson as well. And what we're going to focus on today is solving trig equations, right? And you've done a lot of work just with solving equations in general, right? And you're finding, if we're talking about a graph, you would find a point of intersection or points of intersection. And so it's going to be a very similar idea when we're dealing with trig equations. So this is the homework or the practice that goes with it. So I encourage you, after you watch this video, to go ahead and do some of this practice and take a look at it. But our goal for this lesson is to successfully be able to solve trig equations. So let's get started. So on this first example here, we're going to prove or disprove the statement. If the statement is not for all x, we're going to give solutions on just 0 to 2 pi. So I have this right here, 2 sine squared x cosine x equals sine squared x. So first of all, I want to start off and say, or re-emphasize, that sine squared x is the same thing as sine of x squared, right? So it's sine x times sine x. And just be careful with how you're writing that and indicating that, because if I drop the parentheses, I'd be squaring the x, right? That angle or that arc. So as we get started with this, the first thing that we want to do is turn to our calculator, and we want to figure out, are they equal? Do they ever intersect? If they do, we're going to do a proof and find where they intersect, and then we'll take a look at the domain and just make sure our answers make sense, right? Like, what happens when you plug it back in? Does anything become undefined? And then if they never intersect, we're just going to use our basic algebra in order to algebraically show that they are not equal to each other. So I'm going to go ahead and pull up my calculator. Got a lot of stuff opened. And I'm going to plug this into both of them into y equals. So y equals, that's not y equals. Whoop. Clear these both out. So you've got 2, and you just got to be careful with parentheses here. So parentheses sine of x, close parentheses, squared cosine x. And then parentheses sine of x squared. I need those extra parentheses because I'm squaring the entire thing. I'm not just squaring the x. Okay, so let's go ahead and graph it. And they certainly intersect, right? Like, there are solutions to this. So we're just going to go ahead and figure out where those actually are algebraically. So let's see. The first thing that I'm going to do is I'm going to go ahead and move sine squared x to the left side. All right, you might be wondering, like, why is that? Maybe you are wondering. So think about what you've done before you ever dealt with trig, when we dealt with equations and we were going to go ahead and solve them, right? And things that were squared, oh, those were quadratics, right? This is why we practice so much with factoring. That's why it's so important to be fluent at it. It's built into other things. So once I've got this, I see a common factor that I'm going to pull out. So I'm going to go ahead and pull out a sine squared x, and I get sine squared x times 2 cosine x minus 1 equals 0. And then I'll use the zero product property to set each factor equal to 0. So I've got sine squared x equals 0, or 2 cosine x minus 1 equals 0. So I can solve them both. Right here, I've got 0 and pi, right? So if I took the square root of both sides, I've got sine of x equals 0. When you go ahead and you isolate cosine x, you are going to add 1 and divide by 2, and you get that 1/2. And really, this is asking you, well, where is sine equal to 0, right? You're really using inverse here. Sorry, cosine inverse of 0 equals x, and you're finding the arc that's true for. Same thing here. Well, where is cosine equal to 1/2? And remember, we're working just on this interval for now. So this is just 0 to 2 pi, not inclusive of 2 pi. So where is cosine equal to 1/2? Well, that would happen at pi over 3 and 5 pi over 3. Right, and I can go ahead and check the domain. So these are within the given domain. And then are there any domain issues? Well, no, none of these are going to be undefined, but we could actually go ahead and plug them back in and check. And I know that sine of 0 and sine of pi is 0. So I would have 0 equals 0 for both of these, right? So cool. If you've got pi over 3 or 5 pi over 3, the sine, so think about where pi over 3 and 5 pi over 3 are. The sine is positive at pi over 3 and negative at 5 pi over 3, but it doesn't matter because you're squaring it, right? And so that's why those end up being the same as well. What would happen if we, totally legal math here, but what if we divided by sine squared x right at the beginning? This is something that we've seen before, right? So what would happen if we had 2 sine squared x cosine x equals sine squared x, and then we just decided we'll divide everything by sine squared x, right? This would cancel, and I'd have 2 cosine x equals 1, and I would have cosine x equals 1/2. So I would have lost these solutions, which would have been sad. Oh, that's not a sad face. Why does it have 3 eyes? Oh gosh, that didn't make it any better. Right, so we would have just lost a solution by dividing by it. It's totally legal math, but I just lost a solution. I lost what happens when sine of x, sine squared x equals 0. Right, and that's where we want to remember factoring. Let's take a look at another one. So here we've got solve on 0 to 2 pi again, and we're trying to find sine cubed beta divided by cosine beta equals tangent of beta. So let's go ahead into our calculator again. Ugh, on a roll. Let's see, I'm not going to show this for every single one. You guys are capable of doing this, but I'll show it now. Right, so we want to know what our end goal is in mind. Sine of x cubed divided by cosine of x, and then tangent of x. I know it's beta, but tangent of x. Okay, cool. So they certainly intersect. Again, right? We can zoom in, we could look at the table and see. There might not be like nice values where they intersect though. I could do second trace and find them, but we're gonna do the proof to figure this piece of it out. Cool. Okay, so the first thing that I'm gonna do is I'm gonna go ahead and change tangent of beta to sine over cosine. Okay, so if you notice these two fractions, they have the same denominator. Therefore, their numerators must be equal, right? Realistically, what I'm also could say algebraically I'm doing is I'm multiplying both sides by cosine, right? So sine cubed beta equals sine of beta, and just like we did on the other one, I'm going to go ahead and subtract sine of beta from both sides. You can factor out what's common, which is sine of beta, and you're left with sine squared beta minus 1 equals 0. And then this right here, I mean, I could use the zero product property right now, but it's really good if we recognize that this is just a Pythagorean identity. Right? We know that sine squared plus cosine squared equals 1. So I could go ahead and I would actually have sine squared theta minus 1 equals negative cosine squared theta. Right? So I could right now, when I use the zero product property, say sine of beta equals 0 and cosine squared beta equals 0. Right? So if you have negative cosine squared beta, I'm writing theta, but that's okay, equals 0, then you could divide both by that -1 and just get cosine squared. I'll change it to beta now, equals 0, which is where that's coming from. That's going to be the same place where, let's say you didn't do that. Sine squared beta equals 1, and then you take the square root of both sides, and you get sine squared beta equals plus or minus 1, right? Where cosine is 0 on the unit circle, sine is 1 and -1, right? So now we can solve these. So sine of beta is 0 at 0 and pi, and cosine squared beta, or cosine of beta, is 0 at pi over 2 and 3 pi over 2. Those are the two places that sine was, I should have gotten rid of that squared, is 1 and -1. 1 and -1. Okay, so now our next step is we want to figure out what happens when we go ahead and put these back in. If I put in 0, I think I'm good, right? So I get 0 over 1 equals 0. 0 over 1 equals 0. Cool. If I plugged in pi, I'm going to get the same thing, right? I would get 0 over -1, which is just 0, equals 0. If you go ahead, so we're good here. Check. Pi over 2, I would get 1 over 0. Uh-oh. That's undefined, right? So that's a domain issue, right? Even though it's undefined equals undefined, that's a domain issue, right? So that's going to get kicked out. So my solutions on the interval 0 to 2 pi is just 0 and pi. What about this one right here? So here we're going to be solving for all y. Okay, so let's start off and let's just remember that 2 sine y cosine y over tangent y, what you can't divide by 0. So let's figure out where is tangent of y equal to 0. Well, tangent of y is going to equal to 0 when cosine is 0. Well, where's cosine 0? Cosine is going to be 0 at pi over 2 and 3 pi over 2. So right away, we know that those are getting kicked out of our domain. Y cannot equal to pi over 2 or 3 pi over 2. So if we get those as our result, then we gotta, those are not actually solutions. All right, so let's then go ahead and hopefully you agree with me that right now I could say I've got 2 sine y cosine y divided by sine of y over cosine y. Right, and instead of dividing by a fraction, let's actually multiply by the reciprocal. So I'll go ahead and multiply this by cosine of y over sine of y. Right, and I don't really have this here. So that means that in my numerator right now, I've got 2 sine y cosine y over sine y, right, multiply through, equals cosine y. So some things are going to cancel here. So I can cancel those sine y's, right, these cancel. And I've got 2 cosine squared y. And then if you subtract, just like we did before, cosine y from both sides, I end up here. So a lot of the processes right now have been pretty similar. I'm going to factor out what's common, cosine y, and I'd be left with 2 cosine y minus 1. And then we can go ahead and use the zero product property. So cosine y equals 0, and 2 cosine y minus 1 equals 0. This is going to give me 2 solutions, but hopefully you remember what we did up here, that this wasn't possible, right? So what I'm going to get for this is I'm going to get pi over 2 and 3 pi over 2, right? That's not possible. Like we literally kicked that out way back here at the beginning. And then I have cosine of y equals 1/2. And well, where is, I mean, we've been on all the other ones, we solved from 0 to 2 pi. Notice this one says all y, but let's start with this idea, right? So this is going to be true. And if I just go 0 to 2 pi, on the unit circle, cosine is going to be 1/2 way up here. And what is that? Pi over 3. It's also going to happen down here at, what is that? 5 pi over 3. Ooh, no. But then I want every single time that it's going to lay on top of these, negative and positive. So while I'm kicking this one out, I need to focus on this one for all. And so I'm going to go ahead and do that by saying this, plus or minus pi over 3 plus 2 pi n, right? So what that does is if I guess I'll focus on this one over here with a new color. Excuse me. Pi over 3, if I add 2 pi n, where n is an integer, right? So I'm going to be going around and around and around, and I keep ending up on top of here. Negative 2 pi n is I'm going here, and I can keep going around. But you can go around either way, right? So it's plus or minus pi over 3 for that reason. N is an integer. Right, so it's a little different because it's for all y, not just on a specific interval. All right, so this might be a good place if you haven't, I don't know, tried one on your own yet, that you want to give it a shot. Example 4 here. So we're going to solve this one on the interval 0 to 2 pi. Right, solve on 0 to 2 pi. So right away, do I see any restrictions? No, I don't think so. But sine of 2x minus 1. Now that whole thing is the arc. What do I do with this? You know what? I'm just going to start it off and do what I know. And I'm going to divide by 2. Okay, so I'm trying to figure out, I've got sine of 2x minus 1 equals 1/2. I guess there's a few things that I could do here, right? So I'm going to actually go ahead and factor out that 2. Sine of 2x minus 1/2 equals 1/2. And I'm going to go ahead, and I know that this 2 indicates to me that I have a period of pi, right? We know this. Let's bring back what we know about graphs. So I'm just going to focus in on then, well, let's use some substitution here. So I'll say sine of u equals 1/2, right? And realistically, what I have here right now is that u is 2x minus 1/2. So let's come back to that. And we know this. We know this part. So, well, what is u, right? So that's like saying the sine inverse of 1/2 equals u. Where is sine 1/2 on this interval? Well, it's going to be pi over 6 and 5 pi over 6. So let's go back with that substitution now. So I've got 2x minus 1/2 equals pi over 6 and equals 5 pi over 6. When I go ahead and I solve these, I would have to distribute. Well, no, I guess I would divide by 2, right? Sorry, poor choice in thoughts. I would multiply by 1/2. I guess you could distribute it as well. And that would give me pi over 12, and then I would have to add that 1/2. So I would get that x equals pi over 12 plus 1/2, and x equals 5 pi over 12 plus 1/2. But I need to remember that I had manipulated this a little bit, right? And the period was pi, which is different than the other ones. So even though I'm solving from 0 to 2 pi, what's going to happen with this is I would need to just focus on adding pi to these, right? Because I wanted to go from 0 to 2 pi. So I really solved these. When you go ahead and do this, this is just from like pi over 12 plus 1/2. That's just from 0 to pi. That's just on this indicated period. So I'm going to add pi to both of them for my final answer. And this is the last one that we're going to go ahead and do together. So for this one, what's the first thing that I would do? We're solving this over all x. I would divide by 4. Cosine squared x equals 1/4. There's no domain issues here. When you square root it, you get plus or minus 1/2. So you're figuring out, well, where is cosine 1/2 and where is it negative 1/2? So let's think about the circle. Here you see what it is, but it's going to be 1/2 at pi over 3 and 1/2 at negative pi over 3 or 5 pi over 3. Right, so you're going, it could be either one, and then you're going to be adding. Oh, I'm sorry, and it's negative, so it's at all 4 of these. That's why you're just adding pi. So if I start here and I add pi, I end up at 4 pi over 3. If I start here and I subtract pi, I end up at 4 pi over 3. If I start here and add pi, subtract pi, right? So that's why you're just adding pi, because you don't have to go around the entire circle. You only have to go around half of it from wherever you start to get another point. All right, so that was an introduction to solving trig equations. So I would encourage you to do some practice with this, as well as just continue to practice working with the identities and see if you can start like not always referencing them and see which ones you know really well. But regardless, I would definitely encourage you to continue practicing that and this, and we will see you all soon.